Um, Thank you, everyone. Breaks are always tough. We need to regroup. So I'm very, very happy to welcome Benny Pinkas to the stage. Benny is, I think, one of the most prominent figures in the MPC space, and we're very happy to have him with us. And he's going to talk about his super interesting work in Aptos. Yeah, I'll let Benny take the stage.
Hi, everyone. I'm happy to be talking here. I'll be talking on joint work with Avdas, Alin Tomescu, and Zulun Daniel Siang from Aptos Labs on distributed randomness generation using verified VRFs. This is work we've been doing in Aptos, and it's going to be deployed very soon. So this is like a non-corporate slide explaining Aptos, what the Aptos network is doing. It's a layer 1 blockchain. It publishes blocks of transactions about each block every 1 second. So we achieve transaction finality in 1 second. There are more than 100 validators that achieve consensus on every block. They are located all over the world, and each second they achieve a consensus. The way they achieve it is that token owners, they can stake the tokens at specific validators. And validators that have more than 1/3 of, so the consensus ensures that validators with less than 1/3 of the total stake tokens cannot break the security of the consensus. So the assumption is that the bad guys cannot control more than 1/3 of the stake tokens. So if I look at an image from the Aptos Explorer last week, we had 129 nodes all over the world. The amount of staked tokens were about 880 millions out of something like 1 billion tokens that are available. And this was epoch 6140, which is important because every epoch, which is something like 2 hours, the stake might change. So new validators might join, others might leave, and the power of each validator might change based on how many tokens are staked on that validator. So this is what I said earlier about 1/3 of the stake. It might change because the delegation of stake to validators changes every 2 hours. So as of last week, there were about 880 million tokens staked. The stake distribution changes every 2 hours. And the amount of stake per validator varies very dramatically. Some of them, very few of them, have about 20 million tokens. A lot of them have about 1 million tokens. So there's like a ratio of 1 to 15, 1 to 20 between the smallest validator and the largest one. This is like the only corporate slide I have. The network should run very, very quickly. We have a block every 1 second. In a recent test, it supported more than 2 billion transactions in 24 hours, which is more than 25,000 transactions per second. This is like 13 times faster than what the network of Visa is doing per day. And this was sustained over a full day. And we cannot break this performance. We have to work with it. So this talk is about generating randomness. Why do you need randomness? So the obvious, first example is games. So you can think of backgammon or games like that. But even people who play like action games, kids or other gamers, they want to be sure that the randomness they get, like the boss that plays against them, goes right or left. This is like true randomness. No one is cheating them. So this is actually very important for gamers. And you can think about dice or dungeons or Dragons and Dungeons, etc., things like this. There are other applications like NFT minting, airdrops, selecting leaders for consensus, MEV, protection against MEV, etc., that require randomness. And people want to make sure that the randomness is indeed honestly generated. There's another application I like to talk about, and it's about improving the Fiat-Shamir transformation in cryptography. So what's the Fiat-Shamir transformation? So there are Sigma protocols to prove all kinds of things, like proving the knowledge of discrete logs or equality of discrete logs. And they follow this pattern of a prover and a verifier. The prover sends a commitment, the verifier sends a challenge, and then the prover answers. And there are lots of examples of these protocols. And then the initial protocol, the description is interactive, but to make it not interactive, you use the Fiat-Shamir transformation, which basically says this challenge going from the verifier to the prover, compute it as a hash of the commitment that the prover sent, actually of all of the messages that the prover sent before that, the challenge should be a hash of that, of all the transcript that the prover generated. And then this makes the entire proof non-interactive, just a single message from the prover to the verifier. So this is great. And actually, most proof systems, definitely on the blockchain, they use this Fiat-Shamir transformation. The problem is that in practice, this Fiat-Shamir transformation is very error-prone. There's this paper by people from Trail of Bits and other companies that do audits, and they keep finding bugs in how Fiat-Shamir is implemented. Usually, what you take into the hash function is not all the messages that the prover sent before, and this enables you to completely break the proof. Okay? So that's very bad. So something you can do with on-chain randomness, so the prover can post the first commitment on the block. It doesn't need to compute the hash, because computing the hash is error-prone. I mean, and people keep doing these mistakes when computing the hash. It can wait for the randomness that will be published on the block immediately afterwards, which will take something like 1 second, and then it can post the answer in the next block. So the proof will be non-interactive. It will just take 2 blocks, okay? And the fact it waits for the randomness that is posted on the chain after posting the commitment makes sure that the prover cannot choose the randomness to work with the initial message that is sent, okay? And so this kind of might solve the problems in implementing Fiat-Shamir. And also, it prevents the prover from doing a brute force attack looking for randomness that will make enable it to cheat. So in some cases where a longer challenge means a longer proof, this can actually lets the prover send much shorter proof. So what we want to implement is essentially a verifiable random function, a VRF, which is a well-known primitive in cryptography. The random output should be unpredictable. No one can predict it. And it should also be verifiable, so everyone can verify that it's indeed a true random output. That we couldn't just publish a certain value like 17 and tell you that's the output that was given. You should be able, it was computed based like the initial key that was set when the system was set up. Now, there are external randomness sources that blockchains are using, like DRAND or Chainlink have a VRF. So blockchains can use randomness from external sources. And the question is, why do we need to generate randomness on-chain? So there are several reasons. One is trust. We don't want to trust an external source, both for secrecy, but also for availability. We don't want if, say, DRAND or Chainlink have an outage, then our network will also have an outage with respect to randomness. Another one is latency. So DRAND, for instance, they generate an output every 30 seconds, okay? We have a block every 1 second. Maybe in the future we'll have a different latency. We don't have to wait for DRAND. Suppose that you're playing a game on Aptos, you don't want to wait for 30 seconds till you know what's the next move is. And another reason is how hard it is to write programs. If you write applications and you wait for external randomness, basically the application needs to commit to a future time in which the randomness will be generated, because otherwise it's already known. And then at that future time, it should fetch the randomness. So it's a 2-transaction process, which is much harder to program than just getting random output. So what we achieve is that the blockchain validators of the same blockchain, they first agree on an ordered set of transactions for the coming block. Then they generate randomness for that block, but after agreeing on the order. And then the applications in that block can generate the randomness immediately, and anyone can verify it. So using the randomness is just, like simple programming language. You don't have to commit your future time. Just write a, you wait range. You consume a random value in a certain range. So it should be very simple. So this is what we implement. Now, the way to implement it usually is using a threshold verifiable random function. So the first thing is for the validators to run a DKG, a distributed key generation protocol, to set up the keys for the VRF. And then each validator gets a share or many shares, depending on its weight, its stake, to computing the VRF. Then every block, the validators collaboratively compute the VRF. And to compute it, we need a certain threshold of the shares. And computing the VRF usually is done through intermediate change of computing a verifiable unpredictable function, which you cannot predict. It might not be completely random, but you cannot predict it. Maybe some bits are fixed, which is essentially equivalent to a signature. And then after you compute this verifiable unpredictable function, VRF, you apply to it a hash function that is modeled as a random oracle, and then you get a VRF. And this is what we're doing, what essentially I think most of the applications are doing, of usages of VRFs are doing. So the construction will use bilinear pairing. So just a reminder what a bilinear pairing is. So you have cyclic groups like G, G hat, GT. And a symmetric pairing takes two items from G and maps them to GT. And the property is that if you map G to the A and G to the B, you get the mapping of G and G raised to the power of A and B. Excuse me for being quick. If someone didn't know about pairings beforehand, you won't learn it from this slide. If you know, it might remind you. But you won't be, you can spend half an hour, an entire course learning about them. And an asymmetric pairing takes an item from G, an item from G hat, the blue and red, and maps them to G, GT. Again, satisfying that if you apply it to G to the A and G hat B, you get the pairing of G and G hat raised to the power of AB. And the security of our construction will be based on the bilinear Diffie-Hellman assumption, which means if you have G, G to the A, G to the B, G to the C in G, and the same powers in G hat, you cannot compute the pairing of G and G hat to the power of ABC. Okay? That's a known assumption, a very basic assumption in these groups. So I'll describe how VRFs usually work, and then I'll mention why it's not so simple to implement, because initially it looked simple. So the first thing is to do the DKG, and for that, each participant, each validator shares a secret. So the sharing must be verifiable. We use what's called the Feldman verifiable secret sharing. Each dealer generates a polynomial for Shamir secret sharing, polynomial of degree T. It broadcasts the powers of the coefficients of the polynomial, G to the S, G to the A1, up to G to the AT. And then it secretly sends to each participant the value of the polynomial. Participant J gets the value of polynomial at location J. And each participant can verify that indeed what it got here, G to the, Q of J, if it raises G to that power, it matches what it can compute with the powers of the coefficients. Again, if it's the first time you see it, you won't be able to get it. If you've seen it 100 times, it seems familiar. So, and this is what they do. And if the participant, if he gets a share and this equation doesn't match, then it complains. So this is simple. We learn about it, but it's not so simple to implement. So the first thing is that we assume here that the dealer broadcasts this coefficient of the polynomial. For distributed key generation, we're going to have many dealers. So all of them have to broadcast something. And the degree of the polynomial will be a few hundreds. Okay? So if we have like 100 dealers, each one of them broadcasting a few hundred items in a group, okay, it's going to become very large. Okay? So we don't like it. And the other thing is that if a participant receives a share, it does this check, and the check fails, it has to complain. And then others have to decide, whom to agree with the participant or agree with the dealer. And this is also broadcast. And this is like quite complicated to implement. So we don't want this phase of complaining that the participant has to complain. That's very inconvenient to implement and to do it correctly. Once we have this PVSS, what people usually do is a distributed key generation using Peterson DKG, which basically says each participant shares a secret, as I said before, using this PVSS. Then we see who complained against whom, and then we decide who was not working properly. Then each participant sums the shares it receives from those who were not cheating, and then we have a sharing of a secret, which is the sum of all the shares that were sent from participants which were valid and were not cheating. So this is nice on paper. Again, the problem here is if you want to implement it. If someone receives a bad share, he has to complain. If he complains, others have to decide whether the complaint was correct or not, whether it was justified. Then they have to decide whom to blame, and then they have to sum the shares of those who did not cheat. And this is quite complicated. And then to compute the final output, suppose you use BLS signatures. If you were working in a non-threshold setting, then you had a private key X and a public key Y, which is G to the X. Then what you would compute is age of M, hash of the message, raised to the power of X. And you check the signature using pairing. In a threshold setting, what you will like to do is each participant takes age of M, raises it to the power of its own share of X. X is the private key. And everyone can verify that this is correct using a pairing. And then you combine everything using interpolation in the exponent, and you get the right output. So this is what people usually do. And again, you have a problem here because you're going to get T shares. T is a few hundreds. You have to verify each one of them using a pairing, which is quite inefficient. So this doesn't scale very nicely if T is large. And remember, we have to do these things every second, and we cannot wait a second to compute this. It has to be much faster. So this, I asked GPT to generate me an image of threshold verifiable random function. This is what I got. So there are some problems in addition to what I said before. Our validators are not like that. Each one of them has a different weight. They're not right next to whoever needs to see the output. They are all over the world, so communication might not be very fast. The weight changes every epoch, so every 2 hours we have to change the weight of different validators, and the function must be very fast. Okay, one issue, and I still don't get into the mathematics, is who should run the DKG. So this is also from GPT. These are the validators of the first epoch, and this is the epoch next to it. So every 2 hours, we have the change from one set to the next set. So the reasonable thing is that for the validators of the new set to run the DKG and agree on a key. Okay? That's not very good because doing the DKG might take a few seconds. So this means that the new epoch will not be able to generate randomness in the first blocks that it has, and this is unacceptable. So instead what we do is that the validators of the previous set, they do a DKG and generate the shares for the new set. They can do it maybe 10, 20 seconds before the epoch ends when they know who are going to be the validators in the next epoch. And so they share the keys, and then they also publish the verification key to verify the randomness. Okay, so to do the DKG, each validator shares a secret. The secret, the way it's being shared, we don't want this complaining game that everyone checks the share it receives. If it's not good, it complains. Instead, the sharing will be publicly verifiable, meaning that everyone can check that everyone got a good share. Okay, so to verify the secret sharing, you don't have to blame. I can verify that another participant, Alice, got the right share. So this simplifies the way they have to interact. And the new key is the sum of the secrets shared by validators who sent a good PVSS, and everyone can identify this. The new key should be shared by validators who own at least 1/3 of the stake, and everyone can identify these validators. About identifying whose share to take, so the common implementation of DKG does something like this. These are the validators of the previous set. Each one of them does a PVSS and broadcasts the result. And we use some ordered broadcasts, which we have on chain. That can be on a block. So we have the PVSS messages from everyone. All of them, we publish them on the block. And then each of the validators of the new epoch takes, say, the first PVSSs in this ordered block is the same order that everyone sees, that have a weight greater than some threshold W, and it takes its share from them. So that's the obvious thing to do. However, it's too costly because each PVSS is going to have a few hundred items multiplied by a small constant of, say, 4. You have 100 validators here. It's going to be a lot of items. It might not even fit on a single block. And broadcasting things is much more complicated than just sending a peer-to-peer transaction. So instead, what we do is that each validator sends the PVSS message using peer-to-peer messages to all other validators. So it's not a broadcast. We don't verify that all of them got the same message, but each one can verify that the messages it got are indeed a correct PVSS. Then one of the validators, could be the first one or any other one that we decide, aggregates all the messages it got. And it's important that it'll be able to aggregate PVSS messages from many validators and generate from them a single PVSS of the same length as only one of these PVSSs, and publish it, and then it broadcasts it. And everyone can verify that this is indeed the sum of PVSSs from validators with a weight at least W. And then it broadcasts only a single PVSS, and everyone can verify it. So to do this, the PVSS must be aggregatable, meaning that you take PVSS messages from many validators, you can combine them to a single message, which is like the length of about the same length of a single PVSS message, and it shares the sum of the secrets that they shared. And the only aggregatable PVSS that we could use is due to Gurk and et al. And the problem is that it shares group elements rather than field elements. So what it shares is not a secret A, but a secret something like G to the A in a secret group, so we have to work with that. So this makes using it more complicated. But this aggregatability property is really important for us. So summing it up, we have the validators of the previous epoch. They do a DKG, which is aggregated to a single transcript, single PVSS transcript. This is broadcast. Every validator gets the private key from that published PVSS. And then for each new block, which is every second, they compute the VRF. And the nice thing is that computing the VRF takes messages of constant size. So this validator, if its weight is 1 or 20 or 50, it's always going to send the same length of messages, which is independent of the weight that it has. Okay, so one initial thing we have to do is moving from stake to shares. If we have 800 million tokens, which is the total stake, we don't want to use 800 million shares. It won't be scalable. So instead, we give a share for every B token. Say B is like 1 million or something like that. And the validator, we take its stake, we divide by B, and then we round to the closest integer. And we can analyze and show that the loss of accuracy there due to rounding is quite small. And we typically use something between 500 to 1,000 shares. Performance of cryptographic operations, the important thing to know is exponentiating is fast. Multiplying many exponentiations makes the cost of exponentiations even faster. Doing a pairing is slow. And there's like 2 orders of magnitude difference between doing a pairing and the time of doing an amortized exponentiation. So instead of doing, say, 1,000 pairings, it's much better to do a single pairing and one multi-exponentiation of 1,000 items. You get like two orders of magnitude performance boost from that. So this is what we do. We want to minimize the number of pairings that we use. Okay, so the function we're going to use is something like that. So this h of m to the power of a, this is the well-known BLS signature, which is known to be secure. What we are using as the output is the pairing of h, some generator, h m to the power of a, which if h of m to the a is pseudorandom, then this will also be pseudorandom or unpredictable. Yeah? And the way we're going to implement it is we're going to do a W out of capital, lower uppercase W VRF. You need small w shares out of w shares to compute the function. And the way we do it, the shares will be values of a polynomial. So validator 1 has W1 weight, so it's going to get W1 shares. And the shares are going to be in this format, powers of values of the polynomial. And the master key is the value of the polynomial at 0. And then we compute the function where each validator will send a single message. Can I be like 3 minutes longer? I'll try to. I can be 30 minutes longer, but I'll do it like 3 minutes longer. OK. So I'll just describe how the VRF works. So in the setup, we just generate two generators of the two groups, G and G hat. And as input, we get the weights of the validators. If validator 1 has weight W1, it should get W1 shares, etc. Now, suppose that we have a central guy dealing the secrets. Of course, we shouldn't understand what's happening here just from this talk. But basically, he's doing a Shamir secret sharing, little w out of capital W secret sharing of a secret. And what the validator gets is its secret key is values of exponentiations of its weight number of values in the first group, and the public key is these values in the second group. And that's it. So the total number of shares is the total stake, which is quite large, something like 1,000, which is quite large, but we only do it when an epoch changes. Now, each validator should augment its private key, its public key, so others can verify that it's sending a good input to computing the VRF. So the important thing is that the validator picks a random value Ri, validator I, and then it publishes powers of its private key and also of h raised to the power of Ri. So if its private key here was h to A1, A2, etc., what it's going to take is going to take all of these values and raise them to the same power. Okay, and this doesn't give information. And then he's going to publish this information, and then others should verify that he published the right information here. So basically, okay, this should be the first component of its private key raised to the power of Ri. Also, we have here h to the raised to the power of Ri. The public key also had something raised to that value of this value of the polynomial, so you do a pairing to check this. Okay, we won't go into the math, you just do a single, one-time check with pairings to verify this. Now, the important thing is computing the VRF because this happens every second. So to compute its own share of computing the VRF, the validator takes the input m, its secret key, what it generated previously, Ri, and basically computes h to the m raised to the power of 1 over Ri. This is the only information it sends. And this is independent of its weight. Even if it has 20, 30 shares, it's only going to send a single item. Now, when we get this item, we need to verify that the validator sent us the right value, right? So remember in the previous slide, it published h to the power of Ri. Now it has to send us h of m to the power of 1 over Ri. We have to verify that these have the same exponent Ri in them. We can check this using a single pairing, which is quite standard. And then we need to compute the final output. Computing the final output, you take a subset T of validators whose total weight is at least the threshold that we need. And then you need to combine the values that they sent. So the first thing you do is you verify that they indeed sent you the correct values using the check I mentioned here. And say that this subset T, maybe it has like 20 validators, something like that in it. Then you have to verify, have to kind of work to generate the right output. So this is the augmented public key that the validator published. So it's basically each of its items of its private key raised to the power of Ri. And here you had age of m raised to the power of 1 over Ri. If you do a pairing, then you multiply things in the exponent. So this 1 over Ri here cancels with the Ri there. So basically what you get is the pairing of age and age of m raised to the power of the share of that validator. And then these things you can combine together using interpolation in the exponent. So this is basically what's done here. If you look at the math, this is what's done. And the nice thing is that you only send a single message. Okay. So the setup cost depends on number of shares, but verifying a validator is order of 1, and computing the final output depends on the total number of validators that is used in the interpolation. Now, I won't go into the security. I won't go into the DKG because I'm quite close to the end. I talk about performance, okay? So these are micro benchmarks. The red is ours. The part which is not colored is using threshold BLS signatures with the same threshold. The time it takes and the x-axis is how many shares you have. You see that the signing time in our scheme is constant. In BLS, it grows depending on the number of shares. Aggregation time, both in our scheme and BLS, depends on the number of shares, but it's smaller in our case. And the signature size in our case is smaller and is constant and much smaller than BLS. If you look at an end-to-end evaluation, then the DKG that you do every 2 hours, including the agreement, takes you something like 20 seconds. Okay, this is about the number of shares that we use. And generating an on-chain value takes 160 milliseconds or so. And actually, we have it now running in PreviewNet, and performance on PreviewNet is even better than that. So we can do it every second, and it doesn't make the network wait at all. Right now, we're running a hackathon that different application developers are using this randomness to generate it, build cool apps with it. And we hope to have it running in the main network soon. And that's it.